Okay. Okay. So, thank you for having me. It's a real honor, and I'm very excited to be here. As I said, it's the second tech day that I'm in. I was in your previous one in California, and I'm excited to be here in Barcelona. So, and what I'll be talking about is software-driven control for the software-defined world. I would give you, I'll kind of set the stage. As Steven said, it's somewhat of a nerdy type technical presentation. Hopefully, I'll keep it concise, leaving enough time for Alec to actually show you the product and have a lot of dialogue and questions around the actual things that it's doing. But I think it's really important that we set the stage properly before we dive into the demo. In a way of introduction, as I said, my name is Shmuel Kliger. I am the founder and president of the company of VMTurbo. My contact information is here on the slide. I started VMTurbo in 2009. Prior to that, I was a CTO at EMC. I arrived to EMC in 2005 as part of an acquisition of a company called Smarts. I was a CTO and a member of the founding team of Smarts. We started Smarts in '93. We became the leading providers of root cause analysis for networks. We were acquired by EMC in '05 for $285 million, doing something north of $70 million in revenue in '05. And prior to that, I was a researcher at IBM. So let's talk about what we, if you think about us as IT professional, what are we doing in life? And if you think about it and you step back from the day-to-day details that we are chasing on an ongoing basis, and you step back and put it in perspective, it all boils down to the same fundamental question that we are chasing for years. Since I'm an old man, I mean, as I said, I started my career in 1974 as a system administrator on mainframes in the main computer center of the Israeli Defense Force. And as system administrator there, my job was to actually keep monitoring storage devices, storage disk, and speed, and do all kind of capacity planning and performance analysis of the SICs that we used to do on the disk drives. But if you step away from this detail and you look broader, what is the fundamental problem, the fundamental questions that we are continuously chasing and spending our life on, it boils down to this problem, which is how to assure application performance while utilizing the environment as efficiently as possible, regardless of what we do, whether we do it when we are chasing some application complaining about something that the response time is slow, or if we are chasing an I/O storm on a spindle, or if we are chasing some CPU congestions or ready queue congestions on some hypervisor, we're fundamentally chasing the same fundamental problem, which is how to ensure that the application gets what it needs in order to perform well, while the environment is utilized as efficiently as possible. Or as I like to call it, how to get the environment and keep the environment in a desired state. And if you think about it, the problem is in the way we are go about it and how we are trying to accomplish it. Because if you think about how we do it for years, as I said, I do it since '74, is we are operating in this perpetual loop of, if this is the desired state, the sad reality is that things continuously fluctuating and not staying in that state. So we are operating in this perpetual loop of, okay, let's collect a lot of data. We collect tons of data. If there is anything that we can collect data about, we collect data about. And when something goes bad in the environment, or something goes about to go bad, we're kind of waiting for that to happen, we send an alert or a report to someone that says, oh, we have a problem. And that someone has to scratch his head, bring all his expertise, and trying to figure out what actually went wrong or what actually is going wrong. And the problem is that given that we are collecting all this data, it's not so obvious. Because the nature is that if a problem happens something on your disk, every application that is using that disk suffers. And you get, and because we are monitoring everything, we get all kind of alerts, all kind of reports, everything turns red, and trying to figure out what actually went wrong is not a simple task. And if we are good enough and we are figuring out what's wrong, what do? We fix it. Fixing it, trying to get back to the good, healthy state that the environment was to begin with. And if you step back and you think about what's going on, this part of this loop, this heavy lifting, time-consuming part of this loop, take place when someone is suffering, when someone is not getting what it needs. It takes place when application performance are not assured. So we want to accomplish that, but we are really not accomplishing it, because when we are operating in this loop, we are not assuring performance, because the bulk of the time, most of the time of this loop, take place when performance are not assured. If you think about the whole industry that we are operating in IT operation, you can break it down to two distinct categories. On one hand, you have products out there that collects a lot of data, give you tons of information, some doing better analysis of the information and giving you better data, some are just collecting and dumping the information to the user. And then you have a collection of products out there that deals giving you a better user interface on how to act on the environment. But the heavy lifting, the difficult part of connecting the two, of trying to figure out what actually is the problem based on what's being monitored and what to do with that problem, is left for the human to deal with. And as a result, this elusive goal of trying to assure application performance is not accomplished. And as a result, if you think about it, the environment as a whole has a lot of reds and yellow critical alerts, minor alerts. The environment is not in a healthy state. And the entire goal of what we are trying to do here is to get ourselves out of this loop and get into a mode that instead of waiting for things to break and then fix, instead of reacting to something that happens in the environment, instead of being proactive and react a little bit earlier, trying to take a completely different look at this and say, okay, maybe we can do in software, figuring out what is the state that we want the environment to be in. And in software, drive and control the environment in that state. And if we do it, keep the environment in what we call, keep the environment in a green circle, in a state in which the application gets what it needs, while the environment is utilized as efficiently as possible. And by doing it, eliminate this labor-intensive, constant firefighting, and delivering smooth operations, smooth service with much less effort. Now, before I go and explain exactly how we do it, let me dive for a second and talk a little bit more about this concept of the desired state. And as I said, it's a state that we continuously chasing. And what is that? What I believe is that this is actually a state that the reason that we are continuously chasing it is because it's continuously changing. It's not something, it's kind of an elusive state, an ideal state that we want the environment to be in, but none of us can actually figure out what is that state. So the way I look at it is that a desired state is a state where the application performance are assured while the environment is utilized as efficiently as possible, or in another word, the way that leads to the way we solve the problem is it's an equilibrium in which the workload demand is satisfied by the infrastructure supply. And if you think about that, the challenge with that, and that's why it's an elusive goal that we are all continuously chasing, is that this is a continuous chase of trade-offs in multiple dimensions. If you think about the basic trade-off that everyone in IT is doing, okay, we have budget and costs and QoS on the other side, and we have to make the right trade-off. How much are we ready to spend? What kind of, how much it will cost me, and what kind of quality of service I'm going to get out of my spending? That's one big high-level dimension of trade-off. But there are multiple other dimensions. For example, the trade-off between the demand of the workload and the infrastructure supply. If you want, the trade-offs between efficiency and resiliency, efficiency and performance. Another dimension is the performance of the application and the infrastructure utilization. A very interesting dimension that we'll touch in depth today is this trade-off between compute and storage on one hand and network on the other hand. If you think about it, if we step back and look at the environment, and we take a step back from the details of, you know, the CPU, the I/O per seconds on a spindle, you know, the big forces that works in IT is compute, storage, and networks. And those forces are kind of tsunamis that works against each other, because if you think about it, compute and storage push workloads away from each other, because if I had all the money in the world, I would just put an application on a host with a dedicated host and a dedicated storage and try to say that I solve all my problems. But if I do that, if I have an endpoint or a workload that happens to be very chatty with another workload, and now it has to communicate with that workload sitting on another storage, on another compute, suddenly I may suffer some latency and response time between those endpoints. So from a compute and storage point of view, I want the workloads to be far away from each other, because that will give me the best, quote-unquote, performance that I can get for the workload. However, the latency, the network, is pushing the workloads, the endpoints, to be close to each other. And how do I make those trade-offs? What is the right trade-offs? How much do I put on the same compute storage versus far away from each other to make sure that I'm in the right trade-offs between network, latency, and compute and storage? So those trade-offs, and to compound it, and I can go, by the way, level below, and I talk, you know, how do I make the trade-off between CPU and memory? Should I spend more money on CPU or more money on memory? Should I spend more money on storage or more money on compute? Because each day, each decision that we're continuously making is basically a decision on trade-offs. And to compound it, to make the problem even more complicated, is the realities that we are dealing with, which is nothing is static. Things continuously fluctuating. The demand is continuously changing. It changes by the season, by the quarter, by the week, by the hour, by the second. So this desired state or those trade-offs are continuously changing on us. So even if there was a human that could have figured out those trade-offs based on whatever data we can give him, at some point, those humans cannot keep up with the fluctuations of the environment.
So there's never a desired state?
The desired state is in this elusive state that you're continuously chasing. And my argument is that there is no way that human can figuring out it all the time. And the only way to figuring it out is to let software figuring it out and let software do the work for us, i.e. figuring the desired state and keep the environment in a desired state.
It's still a trade-off. It keeps being a trade-off to keep up with the desired state, because even if you can manage all that thing, you still have a time window in which the desired state isn't there.
Right, but I want to minimize that that window. If I let people minimize that desired state, we'll never get it. What I'm saying is that software can get us to a place where it continues, and you'll see what we are doing. The idea is that we continuously figuring the desired state, and in fact, it's not even the software as one big algorithm that figuring out the desired state. I'll explain how we do it, and then the environment just stayed in that state if you let the software continuously do what it's supposed to do. But you're right. If you'll ask me at the end of the presentation what is a desired state, I don't know.
So what you're basically saying is that you're changing the granularity of the time scale in which you can see what the desired state is.
It's not just changing the granularity of the time scale. What I'm trying to say is that figuring out what is a desired state, it's the dimensions that we have to take under consideration are such that no human can actually figuring it out.
There's too many different parameters for you to calculate the desired state of every virtual machine.
At any given point of time. And that's hard. Even if I'll give you all the time in the world, it's still hard. I'm saying that compounding it is the fact that those metrics and the demand keep fluctuating all the time. That makes it impossible for a person to continuously chasing it. So the way I look at the desired state is actually, if I'm thinking about what is the state of a data center, I'll skip all the mathematical arguments of describing it. But basically, if you think about the state of a data center, if I have to describe to you what is the state of a data center, it's being described in terms of hundreds of thousands of values of metrics. Think about, the memory utilization on host 1, the CPU utilization on host 1, the average and the peaks of that, the memory utilization on host 2 and the CPU utilization on host 3, and so on and so forth. And that's only if I care about memory and CPU, but if I care about network and latency and IOPS and VMem and vCPU, I mean, it's very quick gets to many variables. And if I were to describe what is the state of a given data center, I actually have to give you all those values. I have to tell you This is the CPU utilization on this host. This is the higher utilization on this filer. This is the vCPU on this VM. And it's not enough to describe it in terms of an average, because what does it mean that the CPU average across my environment is 30%? Some hosts are running at 10%, and some hosts are running at 90%. So the average doesn't really give me a description of the state of it. So I have to give you these n variables to describe the state of the environment. So the way we look at it mathematically is that the state of a data center is this point of an n-dimensional space. And a desired state, or the set of states, which I call the desired states, is each of those dimensions, you know, the workload dimension, the hybrid clouds dimension, the compute dimension, the storage dimension, the network dimension, it doesn't matter. And each one of them define a subset of states that are good states, whatever the definition of a good state is. And again, this is very abstract. And not only that, so we have many, many dimensions here. The desired states is a subset of that states, which is the intersection of all of those subsets. So if you ask me what is the desired states, or what is a desired state is a state in the intersection of n spheres in an n-dimensional space. So that's the definition of what we are chasing. And what we are trying to do is, okay, if this is the set of possible states, to continuously making sure, continuously figuring out what is this intersection, and continuously making sure that the environment is in a state that is one of the state in this intersection. Now, let me tell you how we do that. The way the software does it, it's actually not we do it, the software does it, is by representing the IT environment as a marketplace or a supply chain of buyers and sellers. Everything in the IT, from the application to the virtual machines, to the physical machines, to the storage, to the network, to the switches, to the backend storage, to the zone in a public cloud, whether you have containers, if you have containers, to the containers that are maybe running on a VM or on bare metal, regardless of what we have in IT, is being represented as a buyer and a seller. And what buyers and sellers do, they trade commodities, which in our case happens to be compute resources. So think about the obvious ones. A host, a physical machine, is a seller of memory, CPU, I/O, network, ballooning, whatever resources the host sell. Data store would sell I/O per second, latency, storage amount. And again, those are just examples. VM will buy that and will sell vMem, vCPU, vStorage. I can go down to the physical machine, buying from the network bandwidth, and the ports on the switch selling network bandwidth. Everything in the IT buys and sells commodities that happens to be compute resources. And in that representation, we have a notion of price, where the sellers continuously price their resources as a function of the utilization of the resources. So think about a seller, whether it's a host, a data store, a filer. They look and says, okay, I'm selling, I'm a data store and I'm selling I/O per second. What is my utilization now? And if so, this is my price of my IOPS. And in the same time, another storage or another host looks its own memory utilization and says, okay, my memory utilization is 80%. This is the price of my utilization, of my memory. And again, I won't get into the mathematics, but there is a reason why this curve looks like that. It's a fundamental relationship between the utilization of a resource and the delays consumers of those resources will experience. And so the sellers continuously price their resources like that. The buyers, in the same time, continuously shop around for whatever they are consuming. So think about the VM says, okay, I'm consuming that amount of memory, that amount of CPU, that amount of I/O, that amount of swapping, that amount of latency, whatever. Who will give me the best deal for what I'm consuming? And from there, we let the invisible end of the market drive the environment to an equilibrium. This equilibrium is a state. This equilibrium is a state in which the demand is being satisfied, the workload demand is being satisfied by the infrastructure supply. And across the entire chain of supply and demand and supply, from the application all the way down to the fabric. This equilibrium is a state in which application performance are assured while the environment is utilized as efficiently as possible. And by figuring out, by the market figuring out, as part of figuring out that state, it also can drive the actions to get the environment to that state and keep it there. Because think about the obvious. Congestions are being built up on a storage device. The latency on the storage increases. The price of the latency goes up. Consumers of those latencies suddenly say, oh, I'm paying a lot of money for my latency, my I/O access. Okay, can I get it cheaper? If I get cheaper, I'll move there. Keeping the environment in an equilibrium, preventing congestions on the storage from happening. On the other hand, if those buyers don't find a place to move, what does that mean? That the resources that those buyers are consuming is in short supply everywhere in the environment that they can move into. Well, the sellers at that point say, wait a second, I'm making now a lot of money, much more than what I'm spending. Okay, what does a seller do, or a good businessman, what does a good businessman do when he's facing that situation? He says, okay, let me provision more of what I'm providing because what I am having is in a high demand. Okay, so let me provision more of myself. If it's cloning myself or provisioning more memory or more CPU, whatever I'm selling, and whatever is in short supply. And the flip side of that, demand goes down. Suddenly, the seller is losing money on something. And what does a good businessman do when he loses money? He decreases the inventory. He removes some of the inventory. He may close shop if he's losing a lot of money. So the market takes care of itself. So the beauty of what we are doing, and again, it's not that we have some central algorithm that trying to continuously take all the data and trying to figure out what is the state. Each individual entity is a player. Each individual entity makes its own decision. The buyers decide, where should I move? the seller decide, should I provide more of myself or less of myself? And magically, if you want, the environment as a whole stays in a state in which application performance are assured while the environment are utilized as efficiently as possible. And if you step back, and that's the beauty of that, you know, we are chasing a lot of things in life, in IT. But if you step back, there is basically three fundamental actions that we are driving. We are always, regardless of what we are facing, we are asking ourselves, should I add more capacity of something, remove some capacity of something, or reconfigure and place things around, move things around? And that's what we are accomplishing. Now, and what we are delivering to the market is a unified control platform. If you think about all the things that we have from storage, network, compute, and whatever, we are delivering a platform. At the core, we have an abstraction layer that has this market representation, this supply chain that I just described. On top, we have the analytic engine that drives those decisions, which is each entity. And on top of that, we have an integrated platform to plan, control, and deploy workload in the environment. And underneath that, we have a mediation layer that ties this abstraction that for whatever we are managing and bring, if you want, an order to the world of the IT that we are managing.
Can I ask a question, please?
Yes.
Okay, so are you an appliance? Are you integrated into VMware?
So we are a software product, software platform that relies on sources of information and control actions that are exposed by different elements. Like it's a VM that you download and install in the environment.
It's an
OVF, yes, and OVF files, and then we are integrating with VC in the case of VMware, VMM in the case of Hyper-V, OpenStack, KVM, all the different hypervisors. We go down to the storage element, talking to NetApp, EMC. We're going and 3PAR. We are talking to UCS Manager. We are talking WMI and SNMP to the application, or JMX into the applications. So underneath that, we have different sources of data as well as control actions to invoke on the environment. So this is a whole software appliance. And through the mediation, we are interfacing to the environment that we are managing. Now, I really want to rush into the demo. And I know that I'm a bit slower than I should be. So think about us as a software appliance, as I said, and that talks to the different layers, if you want, of the IT stack, including containers like Docker, including SDN managements, SDN environments, and things like that. Hybrid clouds, whether it's Amazon and whatever. And our goal, and our goal is actually to take all of those, both the application running on infrastructure, the viewing and the doing that I talked at the beginning, and instead of looking at each square in isolation, to actually bring all of that together to one control system that continuously keep the environment in a desired state. And let me zoom into one dimension here, because that will be something that we are going to release next month. And I think it's a very important dimension. I mentioned at the beginning these trade-offs between storage, compute, and network. So this dimension focusing specifically on what we call the network dimension. And I think it's a very interesting concept and a very interesting dimension that we are introducing. And if you think about this desired state that we are talking about, what we are focusing now is in this dimension of the network that basically refines the desired state. And as I said earlier, the problem that we are facing when we look at networks is this: okay, if I have VMs that are chatty, they are talking to each other a lot, how far away from each other they can be. Because if they are far away, I'll introduce high latency. Or if you look at any network topology, if I have these pods of servers and I have VMs, like those red VMs that happens to talk to each other, if VM1 is communicating with VM9 a lot, instead of locally talk to it, it has to go from the server, the blade that is on, to the local switch, to the core switch, back to the local switch, and to the endpoints, going to 6 ports. And each one of them is a bottleneck, potentially. And really what we want is to localize them. We want, this is an example, another example, we want to localize them in such a way that the chatty VMs are sitting on the same blade or on the same pod. Again, taking under consideration the trade-offs between how close they can be versus storage, the storage and compute and other things that are available in such a way that the same communication that I had earlier will either now be inside the same server, very localized, or within the same pod going to only one switch. And the beauty of what we are doing here is that all we have to do is add those concepts of vPod and dPod, where vPod is basically a group of consumers, i.e. a group of VMs that happens to talk to each other a lot, and the dPod is a group of localized providers, and we are focusing on that dimension of the supply chain, and suddenly all I'm introducing is a few more commodities that we call flow, which is communication within the same host, communication within the same pod, communication across pods, or communication across clouds. And I give different price to each one of them. Obviously, this is the cheapest one because I want VMs to consume it a lot, and this is the most expensive one. And as a result, suddenly in the market, those flows are being traded like any other commodities that I described before, and suddenly the market will take care of doing the trade-offs between the flows and all the other resources that I have in the environment.
How do you avoid conflicting? I mean, for a load of these technologies, they've already got sort of contention, you know, storage, DRS, NRI, OC. There are various methods already to try and handle contention. How do you avoid conflicting with them?
So if you think about this intersection that I described to you, if you think about this intersection, each dimension is basically making that intersection smaller and smaller. Because the more sets that I intersect, the smaller the intersection become. So now if you think about, you use DRS as an example, but it applies to any of those. What does DRS do? DRS balance memory and or CPU within a cluster, a host of clusters. Okay, this is one dimension out of the hundreds of thousands of dimensions that we are taking under consideration. So if you think about it, a state that we get the environment to satisfy the constraint is in, if my intersection is this state, the DRS state is a superset of the state that I'm in. So if you let us get you to the desired state that we are driving the environment, it's a state that will satisfy DRS, and DRS won't do anything.
So if I've got a given workload running, and then let's say one consumer suddenly goes a bit mad, be it CPU or storage, what I'm thinking, who handles that initial contention? Do the VMware constraints kick in? Does yours kick in? So I can see your view that once you get to an uncontended point of view, and you're looking left, right, and centre for every possible source of contention, and when it's there you balance it, you're fine. You've got to get to that state somewhere.
So at what point the DRS will kick in? When this resource, whatever the resource, will cross some threshold. What this market does, this market will take an action much earlier before you cross that action. So if you are already in a bad state and you cross that action, You just have to let us get you, or following the recommendation that we are giving you to get you to the state. But once you are in that state, every time we probably will react prior to the DRS reacting.
And you're saying that because the ultimate intersection of all the competing variables is so small, you're unlikely to get into situations where you're ping-ponging, for example, like you can with a DRS in an aggressive mode, because you're not just looking at one or two dimensions, you've got so many of them that even if the DRS is not ideally perfect there, it's the best market compromise at that point in time.
Right, but again, yes, the answer is yes, and I would throw back the question to you. If I want the environment to be in a good state, it's not enough to look just on the CPU and the host. I mean, there are so many other things that you have to take under consideration that you cannot say, oh, I'll have DRS taking care of my CPU issues without looking at my IOPS, and so I'll use a storage DRS for the IOPS, and by the way, try to run storage DRS with DRS and make sure that there is no conflicts there. And by the way, there was a product from VMware, I think nobody is actually using it anymore. It used to be called DPM, the distributed power management. Try to do DPM with DRS together, where DPM looks, just by intuitively, you can think about the conflicts that can be generated. So that's why my first point, you cannot do those decisions. You cannot let software make decisions if you look in isolation in a single matrix or a single dimension. The only way to let software, so one way we are trying to do for years is giving all the data for a human and let human figure it out. So I made the arguments why human cannot do that. The same thing, you cannot say, okay, I'll get to that solution by 5 different mechanisms, each one of them looking at one thing out of that. You have to look at the whole, otherwise the software will drive you to wrong conclusions. The only way to solve it is by looking at the demand all the way from the top to the supply in the bottom, understanding the dependencies between that demand and the supply on an ongoing basis, and from there drive the decisions. And that's what the market does for us here.
Yeah, but the demand and in the marketplace, what you already said, can be very fluctuating. So how are you going to leverage that? You say hybrid cloud. Hybrid cloud is something I would use for something bursting very fast, but also going back very fast. So how do you manage that through VM? Yeah?
Well, that comes back to supply and
This
is a very deep question. It's an excellent question, because if you think about it, and that's exactly what we do here, is congestions are built in your internal IT. At that point, you want to burst out to the cloud. Maybe. And if demand goes down and suddenly I have more capacity internally, or took me time, but I got more machines and I have more capacity, I want to bring the demand back. So that's exactly it, what we are doing. Think about the prices in your internal IT continuously fluctuating based on the levels of congestions that you have in your environment. The price of the public cloud, for us, from the point of view of the internal IT, it's an infinite capacity that is available for us on demand. So from the point of view of this, it can be viewed as a flat fixed price. So think about, on one hand, I have a resource, the cloud, the public cloud, at a flat price. And internally, prices fluctuating all the time, right, based on the demand. At some point, prices goes up above that, and suddenly workload moves out. Prices goes down, workload move back. Now, to compound it is, okay, remember this thing. Maybe I have a group of VMs. I don't want to move one VM out of that group because suddenly I'll have latency across clouds. So I have to price that to make sure that if I move the VMs that are talking to each other. And move VMs that can actually run. So think about all the constraints that we put in the environment. They are also commodities that the market deals with. So all of that comes into one single engine that everything is being traded and drive the behavior of those entities.
So the next question is, basically it's a high-speed market trading mechanism that's handling all of those, but that's an awful lot of commodities. And then the flip side is, what are all my remediation possibilities? Because some of that, obviously vMotion, is relatively easy to identify and automate. There's an API, we have everything we need. But I noticed I saw Puppet and Chef go by on one of the slides, integrating new deployments of a whole new web farm or a whole series of web servers. The level of complexity in the price of the remediation and the implementation is not
right. So, this again another question that has multiple layers to it. So first of all, the first question from the market point of view, the action itself is priced. Some actions are easy to vMotion, it's easy, so the price can be very cheap, although I can have a variable price for the vMotion because I don't want to have too many vMotion taking place in the same time. So the more vMotions I have in the environment, the price of vMotion gets more expensive. Other actions are more expensive. And
it's not only about expense, it's also about making sure a VM stays within a certain boundary.
No, but I think
right, so that I thought I answered earlier with the constraints. The boundaries of a VM staying within some, let's say that I want to move VMs to the AWS, but those VMs they must be HIPAA compliance. In the US, I don't know if in the Europe you have HIPAA, some of the, okay, so I can define zones in Amazon that are providing HIPAA compliance. And I can define those VM as required to buy HIPAA compliance. And by doing it, the VM, when it shop around, will look for providers that can sell me HIPAA providers, and they'll move only if the provider can provide me HIPAA compliance. And take the affinity rules, the anti-affinity rules, they are all are commodities that are being traded in the market. So all of that is brought in the decision. So that answer that. But the action is priced, and now you can say, okay, some actions can be automated and executed. Some actions require some human. So they'll stay as a recommendation, and a human has to execute them. And but for example, moving to the cloud. Moving a very stateful application with a lot of storage and memory, it's very expensive and maybe cannot be done. But stateless application, the move is stop it here and start it there. Okay, so we can execute it.
But the trick is quantifying all of the potential remediations. Sounds to me like what's like building a service catalog.
So it depends. So, but again, that is being taken care of by the mediation. The market says, move, or provision more, or remove. Now, in the mediation, we take care. You know what? This is a move of a stateless application. So that move means stop and start.
And that's automatable.
Yes. Yeah. So let's separate. The market makes me the recommendation, then the mediation actually take care of the execution, depends on the environment that we are integrating with.
Okay, that's really rare. There are some things we know we can automate that are probably integrated out of the box, in everything internal to a VMware environment. But as soon as we get into more advanced, more complex remediation actions, that shows up as a recommendation that
needs to be integrated, right? And it can be integrated either with some native tools that exist out there, or with some orchestration tools that companies have in their environment. In the context of open source, we are actually in the process of contributing stuff to the open source to do some of the actions that are currently lacking in different type of environments, both in KVM. We are working with Docker as well, because we believe we can contribute stuff into the containers that will enable us to do some rich management of those containers.